Let me pull up the chat over here. No. Oh, what? Oh, it takes a couple seconds for me to actually go live. One second. Twitch is being problematic. Come on, Twitch. No? Restart Twitch. Okay. Okay, perfect. We are live. Let's, I forgot to launch Zoom. Discombobulated today. Hello, hackers. All right. Let's go live. There we go. All right. Ooh, nice. Someone finished level 6 and 7 right before class. Good job. Okay. What's going on? Okay. Good. Awesome. Man, Twitch is too technologically advanced for my computer. Come on, what the hell? Is it working? Nope. Technical issues. 1 second. There. Now I don't touch it. Perfect. Okay. All right. Let's see. The doorbell. We forgot about the doorbell. Hold on. Very important to turn off that doorbell. That doorbell is a nightmare. The doorbell. Sometimes the doorbell is off. Sometimes it is not off. That's very bad. Come on, come on, come on. All right. Okay. Doorbell is about to be gone. This late in the semester, I'm losing enough sleep that I had to move from tea to coffee. I made myself a Greek frappe. It's very good stuff. Okay. All right, the doorbell's about to be destroyed. 1 second. Meeting settings. One day we'll figure out how to make this permanent, and then we won't have to turn off the doorbell every time. All right, awesome. So let's answer some questions on Twitch and Zoom. They're already flowing in, and then we'll go through the course. All right. We have some advertising going on in Zoom. That's okay. Okay. Question on Twitch. How's my week with all the DARPA stuff? It is a crazy week this week. On the research front, we in the lab here in Arizona State are involved in a number of research projects with DARPA, the people that brought you the internet, self-driving cars, the Cyber Grand Challenge, etc. And it's one of those weeks where we have meetings with, like, here the status is, let's brainstorm for the future. And all of the while, you know, we're preparing the ROP module and all of this. It's just been crazy. According to Steve Jobs, that's my watch, my sleep has been just awful. It's like, you know, about to call the ambulance on me with the amount of sleep I've been getting. It's pretty bad. Okay. So, there's a question. Was last week curved? We'll get to that. Type 1 and Type 2 fun. Yeah, good times. Someone's asking what kind of coffee brew do I prefer. I normally drink coffee socially. Like you would say I'm a social smoker, so I don't know. I don't think anyone says that anymore, but I drink coffee socially. Before the pandemic, when you could go to a coffee shop without performing a complex cost-benefit, risk-benefit analysis in your head, I would go and I would get a cappuccino dry with a tiny bit of vanilla, and I would enjoy it in the atmosphere of the coffee shop, right? And that is how I love to enjoy coffee. I don't just, brew coffee and drink it normally. But I would do that way too frequently. My coffee budget was quite frankly shocking. It is more than my video game budget, and I have a wall of video games, right? So that's pretty bad. But since the pandemic, there hasn't really been an ability to do that. This is a Greek frappe. If you go to Greece, and you are just barely behind the curve of being super hip, I'm told that this is no longer super hip, but it used to be. You'd get a frappe, and it is a blended instant coffee with water and sugar on ice, and then the bubbles are shockingly stable. They're more stable than whisked milk bubbles. And then on the bottom there's water. You mix like this, and then you drink right at this kind of cloud consistency. It's very good. Okay. All right. Dang, people aren't happy with the week extension on Toddler 1. But that's okay because it's over now. You don't have to think about Toddler 1 ever again unless you want to go back and make it up. Let's see. I am not Greek. I was born in Russia. All sorts of mixed ethnic descent, and now I am American. Except for I even drive a Jeep, so Wrangler, and the roof fell off while I was a grad student, so I drive a Jeep without a roof. Okay, anyways, okay. Question: is this still a hacking class? It's still a hacking class, but I was talking about coffee. I'm geek, not Greek. That's good, exactly. Awesome. All right, well, I'm glad that the extension actually at least helped people keep up with their other classes, if not directly helped their grade on this class. Okay, awesome. So, let's talk about where we are in the course. So again, the tagline of these, and I always forget to show this title slide because then it's a pain in the butt to get to the actual update, is don't panic. It'll all be okay in the end. Well, the end might just be far away. Okay, cool. Oh man. Someone on Zoom is waiting for me to join in Among Us. I actually finally played Among Us. I'm a big fan of games like Avalon and so on, the board games, and Among Us captured that quite well. So I felt bad that I hadn't played it until recently. Okay. You guys can hear Baby Yan crying. Baby Yan's going to join us for part of this lesson. Mrs. Yan is picking up Petrie from the vet. So, okay. All right, let's dive in. First, of course, the meme review. I always forget in the meme review to leave room for myself. The bottom row of memes here is all about how the course is apparently wrecking people a little bit in certain situations. This one right here, this meme was actually called Yan.gif. Yeah. This, it kind of makes me happy with how the class is going. The roller coaster of you see a new concept, you worry. You're like, I'll never be able to master that concept. And by the time the week is over, you have learned it. Through this sort of practice makes perfect push. It's awesome to see you all start to become more and more proficient at hacking and do better and better at CTFs for those doing CTFs for extra credit and understanding the concepts. That is great. All right. This one is pretty good. If you recall back when we did Baby Suet and challenges were, solutions were a dime a dozen. You just boom, 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 boom. Now it's heavier going with the final challenges getting like 15, 20 solves. The difficulty is definitely going up, but people are rising to the challenge, which is awesome. And I realized we had kind of like this GIF shows this 1, 2, 3, 4 punch. I would say that we're gonna step back and take it easier. I don't know if that's necessarily true though, but Baby Rop is gonna be a fun module. And then this one is good. I don't quite fully grasp that meme, but yeah. All right, we have this meme I put in. It was from last week as a reminder that election season is now, not today, but here in the next couple of weeks. Remember, AT&T syntax bad. Go vote. You can vote early in Arizona, and if you're eligible, obviously. So do it. Awesome. People's ballots coming in the mail. This is great. Okay, cool. I've been personally getting texted by people encouraging people to go out and vote constantly. I got three different texts today from 3 different numbers. A couple yesterday. I'm going to start a group chat with all of them, I think. That would be good. For those writing me in, you can try Zardis instead of my last name. But I wouldn't recommend it. I'd recommend voting for an actual candidate. First time I voted, when I was in college, I think I accidentally wrote a candidate in because the voting machines in New York were insanely complicated. It was like a Rube Goldberg machine built in the 1800s, and there's like a lever here and like a little pulley slide for right. And anyways, that's neither here nor there. I think this meme was about some of the later toddler challenges that required precision, specifically in, for example, Toddler 1 Level 8. Getting a knob sled in there would be quite difficult. You have to actually be fairly exact. This one is from last week, but I put it in here as a how to say it, an inspiration. And then you guys are amazing. You're solving toddlers left and right, and now looking forward to the ROP. This is a great ROP meme right there. That's pretty good. All right. Someone said, "What is the origin of Zardis?" The origin of Zardis is that when you ask a 12-year-old to come up with a nom de guerre for themselves, you get really stupid stuff like Zardis. All right. So, CTF report. This past weekend, 15 students played Hacktober N1 or Macker CTF, which is really cool. It's a little down from the previous weekend, but I think people were just, pushing hard on the toddlers. That sounds kind of weird, but, pushing hard to complete the toddler challenges. The Hacktober CTF specifically was really cool. It was super approachable. As far as I could see, there are tons and tons of challenges of different skill levels. 2 teams that weren't Shellfish. Shellfish played Macker CTF, I think, predominantly, but 2 of the 466 teams, I should probably just call out the team names. I'll see if the team members mind, but 2 of the 466 teams solved over 30 challenges. This is incredible to see. I'm super proud of you. That is awesome. So someone's already bragging that one of those teams praised the yellow box. That's true. Good job. Okay. And then next weekend we have quite a choice. We have Hacklu CTF. It's a long-running 2-day CTF hosted in Luxembourg, I think. Now that I say it, I'm nervous I'm going to get that wrong. Let's see the LU domain. Yeah, Luxembourg. Awesome. So, I haven't heard of Razi CTF. Seems to have fewer teams registered according to CTF time, or fewer teams clicking the I will participate button. Hack the Vote CTF is organized by my alma mater, my undergraduate institution. I went to Rensselaer Polytechnic Institute, now home of RPISAC, but I'm way too old for that, unfortunately. They started up shortly after I graduated, but they are putting on their CTF, and there is a number of other CTFs. If you go by the teams, then the most teams will participate in Hack the Vote, then Hacklu, and so on. But click through, read the philosophy of the CTF. This is just a screenshot from CTF time. Go for it. Also, PCTF, PEA, not PEE. Let's take a quick look. PCTF. Cybersecurity competition for high school and college students. So this sounds pretty right in that area of CTFs that might be very approachable. So that's 5 CTFs, 6 CTFs to choose from. The CTF field is getting pretty awesomely large, so that's really cool. Okay, awesome. Let's talk about the leaderboard. So the leaderboard shifted since last module. So this module was 2 weeks long. At the end of last week, I think the top 12 or so were locked in place. Now this week, the top 18 on pwn.college have solved all challenges, which is pretty awesome. Hold on, let me move my video there so you can see all of the scores. So congrats. Let's see. Some people that are used to being up there. Obviously, Frickmod, Nop Nop Goose has been there for several weeks now. 01 is constantly near the top. So if you look, 01 went from first to third. Nop Nop Goose, but everyone was tied for first in some sense. Let's see. 0 was already in the top 20. Torah Shulk was already there. Etsy Shadow Lightning was there. Dereference Null Pointer was there. Hollow Circuit was there. Janitor Jeff has been there in the past, but wasn't there last week. So Janitor Jeff has caught up. So that's cool. MK was there. Root was there. Neural was there. There were all of the memes of Neural being OP and we need to nerf Neural. So far we have failed to do that. Propio is up there, and MSM is a new name in that top 20. Flynn was there, yeah, Flynn. And Blue Shirt Jan, of course, the one and only. And Shinjay joined the Masters of Hacking by solving the JIT-ROP challenge. So the top 18 solved all challenges. I actually haven't looked at which challenges the 19 and 20 haven't solved. Euron and Cascadian. But Cascadian, you gotta push hard. You dropped from that tied for first position. Got to get back up there. But these hackers have all solved the JIT-ROP challenge, Toddler 1 level 8, or not JIT-ROP, JIT spray. We'll get to JIT-ROP one day. Super awesome. That challenge was all mitigations turned on, everything basically no holds barred, a simplified real world scenario that you might see exploiting something like Google Chrome. Super awesome. All right, so let's see what we're talking about. Yeah, probably catching up on sleep is a good point. So great job everyone in the top 20, everyone else in the course, obviously. You've been doing super great. Let's look at grades on that note. Well, that's getting to be kind of unreadable. All right, so we started out with 209 students at the beginning of the semester. We still have 127 of them registered. That's down 2 from last week. 111 solved any of the Toddler 1 challenges. Would have liked to see more solves, of course. Ideally, 127 people would have solved any of them. That's okay. These things happen. The grade distribution for Toddler 1 is interesting. So over almost 75% of the class got below 50% on Toddler 1. That's, of course, not what we would like to see. People seem to have skipped the A grade, so it seems if people figured out well, that's probably how the percentages worked out, because there were 8 challenges. Yeah, so yeah, that makes sense. So this is the number of people that of ASU students, of course, that have solved the JIT-ROP at level 8. This is probably up to level 7, and then less and less over here. Definitely a tough week. It's tricky. What has this done to the grade distribution? Well, normally without the curve, it has dropped it quite a bit. So this is the uncurved distribution here. If you look at this same thing last week, so these are last week's grades, and then this week's grades. It dropped a lot of people from an A to a B. Dropped some people down into the D and E area, and of course, but that's without the curve. What we're doing is updating the curve fairly aggressively. You're all putting insane amounts of work into this course, and we're not going to let you put in insane amounts of work and then fail when you shouldn't, when you deserve to do well, because you've learned a lot even if you weren't able to do JIT-ROP, right? So last week, again, this is last week, the spread was I think 11% for B, 14% for C, 14% for D. This week we're moving it up to 15%, 15%. So this makes something closer to a bell curve. If you combine A and B, it actually does look like a bell curve. Actually, it looks more like a middle finger. But the bulk of the class is getting Bs, almost half of the class. And then another half of the class that's getting A's or C's, or not another half, like whatever. There's like a third of spread. Okay, how many? So let's catch up. There's been quite a discussion. Are we still going to have a Toddler 2 week? Yes, we will definitely still have a Toddler 2 week. Expect Toddler 2. There'll be awesome JIT-ROP through Yan 85. It'll be great. You'll love it. Okay. How many hours am I expecting students to spend per week? I expect students that have come in with the necessary prerequisite knowledge. We're talking about x86 assembly and good knowledge of C, a good knowledge of Python, and a good knowledge of computer architecture. 20 to 30 is possible. Like I said in the beginning, if you don't have that prerequisite knowledge, can be a lot. We're looking at various things to do for a future semester. I mean, I would love to make this a 6 credit hour course without changing anything. Then I think it would be, maybe even a little too easy, but maybe it'll be right there. But we'll have to figure all that out later in the semester alongside the official course evaluation that ASU sends out. I will send out a survey to see how many hours per module people spend and so forth, just to help us modify things accordingly. Let's see. Yeah, so some comments that ASU doesn't quite have the prerequisites taught anywhere. There should be mostly taught, they should be taught in computer organization, but that's a separate topic. They should also be taught in 365. So 365 goes over x86 assembly and even touches on ROP and stuff. And that is a prerequisite for this class. And let's see. The difficulty of the concepts. The difficulty gets in the way of understanding the concepts. Yeah, it's. I think we could have done better, especially in Toddler 1, of a gradual increase in difficulty level of the challenges. It's tricky, right? So every year I have, 1 or 2 of my students. I think this year I have 3 of my students in the course, right? And depending on their research area, my graduate students, depending on their research area, they complain that the challenges are too easy, right? So it's hard to balance the difficulty. There's a concept that you have to wrap your head around, usually for every level, and there's only so many things that you can do to make that more gradual ramp up in complexity for that concept. A lot of people are saying that 365 didn't help with this, which is concerning. Could you take 365 with? 365 definitely didn't make you use MIPS, and it for sure uses x86 64 because I've taught guest lectures. Yeah. Let's see. I'm trying to keep up with the Twitch stream. I'm still new to the streaming life, so sorry, with the Twitch chat. All right. Really? You didn't have assignments to like buffer overflow x86 and stuff in 365? Okay. Oh, interesting. Yeah, someone did. Okay, anyways, we can have this discussion later. We should have this discussion. I should actually really have another discussion with Adam to make sure everything flows. Okay, awesome. Yeah. So buffer overflow in 365, and then this class builds off of that, completely ramped up. But we will definitely... oh dear. I lost my job and house keeping up with this class. This is all good feedback. I will send out a feedback form closer to the end of the class because I would love to capture all of this and to take it also to the administration and said, hey, look, this class should be 6 credit hours so students can really focus, or something along these lines, right? So we should see. All right. The point is, we got you. This was a hard module. We adjusted the curve. As a reminder, the grade cutoffs can't go up faster than 1 point per week. Don't panic too much. There's 7 weeks left, 6 weeks left. Did I make a mistake with this? 6. There should be 6 weeks left, I think. Anyways, 6 weeks left. That means a C, even if everyone starts doing amazingly, and you should, and I have confidence that you will. I think the C won't be able to get back up above 66. Okay. Theoretically speaking, a minimum grade for a B could potentially get up to 81, but I don't see that happening. I'm not gonna shrink the grades, the grade spreads. There's no reason to. Okay. Anyways, moving on. All right. So, what do you do if you are not doing as well as you would have liked? Don't panic. Panicking is natural. It's part of the process. You can start out panicking, but then don't panic. Eventually, as you turn that panic into knowledge by learning the material. All right. Don't forget that challenges are still worth half points after the deadline. There are some students that have quite a lot of baby shell that they could still make up using the knowledge of x86 assembly and so forth that you have now acquired by participating in this course. I'm sure that you can go back and destroy baby shell, right? And that can be a significant boost. We'll still have a makeup week right at the end, but I understand that it's tricky, and we'll have 1 week with a light assignment. I'll talk about that in a sec. That's voting week. Oh, 1 second. Baby on arrives. Hold on. Oh, thank you. All right. Actually, let me put her so I can see her on the webcam. See her on the webcam? Yes. Perfect. Mrs. Yan has to go pick up Petrie from the vet because he has a tumor that was just removed that we're biopsying. So, yeah. Anyways. Petrie is my cat. Yes. Exactly. No, Petrie is not Baby Jan's name. Yeah, PD is, hopefully he'll be okay. The biopsy hasn't arrived yet, so. Alright. Cool. While the baby lets us concentrate. Alright, the other things. CTF extra credit is still on the menu. Some people have emailed me and saying, hey, I participated in a CTF, but I didn't really solve much, so I didn't send in a write-up. You don't have to solve things. You can solve things or participate for at least 8 hours earnestly, and send in the write-up to either effect. If you should be able to talk about what you did, what you tried, what challenges you worked on, and so forth. But it's a participation trophy. In proper millennial fashion. All right, and remember, we extended the Y grade option. We're just YOLOing it basically all the way to the end of the semester, like the day before the last assignment is due. The Y grade means C or better. If you get an A, B, or C in the course, you get Y if you choose to do so. This doesn't impact your GPA, So as long as, if we ended this week, where's my, there, if we ended this week, as long as you have a 60% or better in the class, which is if you, let's see how it works. If you have a 15% or better in all of the assignments, and then you go back and you do the rest after the deadline, you will have a C in the course. If and it ended today, then that won't impact your GPA. It'll count as a pass and satisfy all requirements where you need a C or better. If you get a D or an E, you still get a D or an E. It's not a pass, no credit. It's a YDE. Okay. So what else? I think that's it. And yeah, so the makeup, always feel free to ask for help on help. I think we'll also have scheduled collaboration hours. One thing that I noticed was we had collaboration rooms open and available all week. Actually, this entire module for the last 2 weeks. People haven't been using them as much as I would like to see. One thing that we're going to try is to keep them open for the ROP module as well. Go ahead, collaborate on the concepts. Don't exchange code directly or a solution code directly. You can say, here's a snippet on how to use pwn tools, of course. But collaboration rooms will remain open, and we will schedule, maybe you'll say, okay, at 6 p.m. every day, we'll have official collaboration hour where, just to give people some additional help. And you can, of course, work on makeup during the collab week as well, because I have no doubt that you will grasp these ROP concepts and go and be in a great shape. Okay, so what are we doing this week? We're doing ROP. This week is going to be super awesome. Hopefully you saw the lecture pre-stream, and now you understand just how straightforward the concept of ROP is. It's great. The baby agrees that ROP is great. So we're going to do ROP, traditional week-long module. We're going to have I think 12 levels of challenges. We'll launch the first 6 or 8, I forget, tonight. Launch the rest tomorrow night. Next week is the week that includes voting week for the course, or voting day for the course. So from 10/28 to November 4th, and November 3rd is voting. So we're going to have a light week. Originally, this was going to be a makeup week, but by expanding binary reverse engineering and the first wildcard slot, we had to sacrifice democracy. Hold on, guys. I'm going to lecture from here while I get the baby into a situation that you will be happier with. So, what we're going to do for the democracy week is start you off on the concept of not quite kernel exploitation yet, but interacting with kernel code. Kernel exploitation itself, we will save until Toddler 2. So most of the Toddler 2 challenges will have both user space and a kernel component. And what that means will become very clear next week. But for the challenges next week, we'll probably have fewer levels. Oops. Okay. There we go. Very good. Okay. Now we should have some more time before she freaks out. All right. There we go. So, we're going to have for this next week fewer levels. We're thinking right now about 4, and they will really be interact with this kernel module in this way. We'll probably provide source code for the kernel modules, excuse me, and just keep your workload low while conveying the basic concepts around kernel interaction, so that then we can go on and in this wildcard module 2 really explore security problems in the kernel. So that's what we're thinking right now. Cool. Okay. And that is that. Okay. Let's catch up on questions on Zoom and stuff. And then I need to talk about a couple of concepts that from questions I've gotten I need to discuss in this extended Q&A, and then we'll launch the challenges. All right. Any questions on Toddler 1? I don't think we have time to go through maybe until we launch the challenges and start to collab, and then we can maybe look back at some of the challenges. But any questions on Toddler 1 before we roll on? Oh, what were the plans for the Toddler 1 levels past 8? We had one, didn't we? Oh, we were thinking of let me try to remember on Little Sleep. So one thing that I wanted to do was to have a JIT spray challenge where the code wasn't at a known location, right? So right now in level 8, the code is always mapped at 1337000. If the code was mapped with the argument to the first argument to mmap being 0, it would be mapped right up against the library somewhere in an unknown place. This would, of course, complicate things for you when you and depending on how you did the attack itself, it could complicate how you redirect control flow. You'd have to think about it a little more. The other things that we didn't release just because, I mean, it was 8 was plenty, is if you recall in Baby Jail, the final challenge was this parent-client jail that you had to talk from the client into the parent to get the flag. Something similar with Yan 85, first of all, and then second of all, something similar with a vulnerability in the parent that you had to exploit from the client. This is a scenario that occurs in browsers as well. So you have that parent process that is super privileged, and the child processes that are sandboxed, and you have to either from the child process attack the kernel or attack the parent process. Yeah, and then but the real thing for more levels in Toddler 1, I think we should probably have just step by step a smoother transition. I think we optimize for having fewer levels for you to deal with, but then the levels themselves had a little bit of a higher jump. Cool. So, hold on, I'm being attacked. Okay. So, okay. Let's move on to 2 concepts in return-oriented programming that we did not cover in the lectures that are relevant for well, one of them I kind of covered, and I'll start with that one, and then another one I'll mention right now in a sec. Okay, so Let's get this away from this GIF that's distracting. Awesome. All right. Baby Jan is indeed the brains behind this operation. Okay, so let's say we have my ROP example here that I talked about in the course, right? In this ROP example, I compiled it with no stack protector, and for the most part, the challenges that you'll be interacting with will, for the most part, have canaries off. Usually won't have a PIE. They'll all have a non-executable stack. Some of them will have PIE. Some of them will also have canaries. But you know, obviously, you'll need to leak out the canary and so forth. All right. So we compile it, we run it. I mean, you've seen me do this on the lecture. I give it an input and it's segfaults, right? There's a couple of interesting things here. On the lecture, of course, I think there's in the second lecture, the Lego lecture, I combined these two Lego blocks essentially to trigger this and this. And I got lucky because the program had the functionality in large kind of blocks. Like on the large scale, the program already opens /flag, and then I return to something that does a send file, right? You don't always or even frequently get this lucky. I mean, realistically, if you're exploiting something large like Google Chrome, you will get quite a lot of built-in functionality that you can exploit, but you can't really count on that. So what would you do if instead of send file, this program did open and close? Right? Suddenly this example becomes very, very, very different, right? Or, I don't know, let's say it did, instead of any of this, it just said that, right? So all it has is puts. So now this program has open, puts, and read. Actually, here, what would we do? Well, we would ROP through and we would call open, then we would call read, and then we will call put. There's still not a problem, right? Because we can still print out the flag. What if we no longer have open? Now we just have read and puts. Or worst case scenario, what if we don't even have puts? We just have read, right? Let's change this to 1000 to simplify things. Or, hold on, I just realized we need the puts for what I'm about to demonstrate. All right, so we have a trivial overflow, and then we have a function that calls puts. Okay, let's start up IPython in screen. Okay. What is going on? Sorry, checking up on if I'm missing any good chatting on. If I'm missing any good chatting. Okay, question is, oh, Jan, have I considered taping an iPad to the back of my head? That might be a really good idea. I think in maybe a couple of months. Okay, why no Tmux? I'm just a big fan of Screen. I'm a traditionalist in that regard. I have a Screen RC that is 300 lines long. So yeah. Okay. So How are we going to interact with this thing? Of course, home tools. We can. I'm going to show you how to, interact with a process by wrapping. All right. First of all, actually, let me give you a summary of how we compiled it and everything. If I do checksec, this file, no stack canaries, and no PIE. What does no PIE mean? It means the code of the main binary is not position independent. This is a huge, what's it called? The things when you're bowling, and the gutter guard. It's a huge gutter guard because obviously this gives you a whole lot of parts of the code that you know how to the location of, so that you can use it in your return-oriented program. All right, so we launch this ROP example every time. All right. We launch the ROP example. We're going to send it a bunch of A's. So let's see. Let's take a look at the disassembly. Didn't we figure out, first of all, sorry about the, there we go, and didn't we figure out how to disassemble a single function? Yes, -d symbol. Nope. Maybe over here? No, okay, I give up. All right, it's fine. We'll disassemble everything and then, as always, scroll up like a jump. What is going on? Baby. Okay. All right. So, I hope that's true. All right. Here we are. This is what we're up against in terms of the vulnerability. We have a push of the saved base pointer, the setup of the stack, and the stack is, there's a hex 16 bytes of a stack frame, after which, so you have your stack mirrored, right? So you have your stack, 16 bytes. To the right of that is the saved return pointer. Sorry, the saved base pointer. To the right of that is the saved return address. And then we call read into that. So there will be 16 bytes of padding, 8 bytes to override the saved base pointer, and then the rest is your ROP chain. So it's 16 bytes, 8 bytes, plus our ROP chain. All right, now what is our ROP chain? Our ROP chain can be quite a lot of things, but first let's just try this functionality that puts out hello, and then you'll see why I'm talking about this. Where's our, yeah, it was bar. So we're just gonna call bar directly, and bar will just print out hello. All right, so our ROP chain is going to be not much of a ROP chain. It's just pwn this and the address of bar. Okay, and then we read all, and here it is. It prints out hello. Что такое? I think Bebe is getting. I'm gonna have to lecture like this, guys. Bear with me. I think this will keep her just marginally happy for a little bit longer. Actually, real quick, we're gonna check. Do a quick diaper check. Diaper check. What's going on? Where's the diaper? No, diaper's okay. Don't panic. Okay. Oh, disassemble equals main. Thank you very much. So now we're amazing. Okay, that's a lot. Easier, I don't have to scroll up. All right, disassembly equals main, disassembly equals bar. Here we go. All right. All right, so this is already return-oriented programming, strictly speaking. You're returning somewhere to reuse some functionality of a program, right? What else can we do with this? How do we read the flag? We figured out how to call, output hello, but there's not much else right now. We haven't figured out how to, call open and send file, right? All right, well, that's not a problem. We can, of course, look at where in the code, if we, let's launch up Binary Ninja Cloud. She usually puts up with this. Oh, Chrome just crashed. What the hell? Это ты сделала? I think Baby Jan just crashed Chromium. It's gone. Okay, restore. Okay. Fascinating. All right, let me reset this up. That's not my slides. That's where the slides will go. All right. Let's go to Binary Ninja. We're gonna upload a binary. Where is it? Phone. ROP example. Continue. All right. So our goal, if we choose to accept it, is to launch send file of our flag after we open it, or some other way of reading the flag. We're not, super picky, right? As long as we get the flag, we're happy. But there is seemingly very little functionality in here that will call something like read. Something like open or send file, right? In our original ROP example from the menu slide, from the lecture, from the Lego lecture, this binary has functionality that'll open the flag and functionality that is send file, and that's what we use. Here, we no longer have this, right? So what do? We can, of course, look at other... All right, guys, hold on. I'm going to see what's going on with the baby. 1 second. I apologize about this. Okay, что такое? Что такое? Okay. No. I don't think she's got a wet diaper. She doesn't have a wet diaper. Does she have a poopy diaper? No, we're good. Okay. All right, we're gonna have to. All right, let's see how much time we can get out of this. Yeah, that way. Oh. Okay. Baby Jan's on the bouncy chair. All right. This should give us a couple minutes, and by then, hopefully, Mrs. Jan will be back with Petrie, and we can Good. Have some sanity. Okay. So, no clear functionality to open and read the flag in this binary. What are we going to do? We're going to make our own functionality to open and read the flag. Here is how, right? Normally, the first thing you do, you get your ROP gadget finder and you start building a ROP chain. So we say, okay, give me unique gadgets up to 2 in length in this file of ROP example. And look how few there are. Because it's a tiny file, unfortunately. So now we have kind of a small set of things. Let's see what can we do. We can set RDI, right? If we have a gadget to do RDI in ret, that's great. We can set the first argument to a syscall. We can set RSI and ret. That's also cool. We can set the second argument to a syscall. We can shift the stack and ret, like as a sort of janitorial gadget to clean up the stack. Leave ret. This will pop RBP and move RBP. First move RBP to RSP and then pop RBP. That's good. What else? I mean, there's not a lot of useful things, and one thing that is very much missing is syscall. In fact, as I mentioned in the slides, you're very rarely going to find a syscall gadget in a small binary. In a large binary, I mean, if you go start looking at bin bash, you'll find it, right? But in a small binary, it's very rare to find. Okay, so now you have your gadget collection, and the only immediately useful thing we saw is pop RDI, pop RSI. First argument, second argument. We don't even, in fact, have a way to pop RDX, which is the third argument. So, right, so you couldn't even, or RCX or R10, depending on what calling, if you're calling a syscall or if you're calling a library function, which is the fourth argument, right? That's bad news. All right, baby's trying to bust out of that chair. Okay. Okay. So, you know, the baby is usually very, very well behaved until it's class time, huh? Good. Okay, cool. So, this on the face of it seems problematic, right? Because we don't have a lot of things to run. But let's dig a little deeper, right? ROP example, actually, if we run ROP example, and we look at what is mapped, obviously the binary is mapped in at a known location because it's not position dependent. Then we have a lot of libraries. We have libc and libld. Both of these have executable code, and that executable code can also be ROPed through. Okay. No, she doesn't like that. Sometimes she likes it. Okay. That executable code can also be ROPed through. And just like normal, just like a normal binary, we can look at the gadgets in a library. Why not? It's just code in memory. And there are a lot, right? There are a lot of gadgets in libc. Gadgets for everything. In fact, we just saw a syscall over here. Cool. I am absolutely positive that we also have gadgets to pop RDX. There we go. Pop RDX. Where's my ret? Well, pop RDX, pop R12 ret. So we have a gadget that will set RDX and R12 for us. All right, so we have, I mean, this is plenty of gadgets to do more or less anything that we more or less anything that we want to do. Okay? So, let's see if she'll deal with the chair. So our goal is, if we can't do everything we need from the binary, there are libraries in memory. Of course, the problem is, if we relaunch this, the obvious problem is ASLR. If you look at these two different runs, here, even though the main binary is at the same place because it's not position independent, the libraries are in different places at every run. And there's way too much entropy here to get lucky with a guess. Right? So the code in the libraries is, whenever we restart the process again, is located at completely random places, which is bad news. So how do we mitigate that? Obviously, you've dealt with ASLR before, and the solution, I kind of wish the class was in person with low latency, but the solution, of course, is to leak out the address of libc. How do you leak out the address? Using some functionality in the binary, subverting some functionality in the binary that will leak. Hold on. That will leak out. All right, I have an idea. We're gonna sit her down, and there we go, and give her something non-harmful to play with. Oops. There we go. Okay, cool. All right. So, we need to reuse functionality in the binary that will output something. And that functionality is right here. I was very careful to make sure puts was in the binary. If you recall, I took it out briefly and then I put it back in. And that is why. So how do we trigger puts to print out the address of libc? All right, first, how do we trigger puts to print out anything? Okay. Obviously, it doesn't show up here, but if we disassemble the binary, specifically the function, let's just disassemble the whole binary. There are two ways to call puts. One way is to jump into bar, where bar calls the imported, now that's dirty. Bar calls the imported version of puts in the binary, right? So bar will call puts, if we jump into bar with RDI, bar takes no arguments and it just calls puts on a string of hello, and it loads the address of that string into RDI as the first argument to puts. But of course, nothing's stopping us from jumping to here, which will then call puts to be called, which will, and if we had carefully set RDI, which we can, we have gadgets for that. We have gadgets to set RDI, so we can set RDI to a memory address, and then puts will output all of that memory address up until the first null byte, right? So right there, you can get a leak. So let's weaponize that. Actually, let's first simplify it a little bit, because here we'll call into this puts, and we got really lucky because the function returns right afterwards with one extra pop. But it didn't have to do that. It could have done some other stuff that would be very hard to survive. For example, imagine if the function called puts and then immediately called exit. In fact, let's make it harder on ourselves. And let's make it do that. Manila. Ooh. No. Hold on. Okay. One sec. Let me see if Mrs. Yan is back. Okay, hold on. Okay. Insane. All right. Baby Yan didn't fall for this, just like Lego's trick. Okay, so we're trying a new station for Baby Yan. Yeah, now she's happy. Okay, cool. All right, let's recompile our ROP example. Mrs. Yan is almost home, so baby will be happy in a second. Oh, I think she just got home. Whew. Okay, cool. So, we have a new ROP sample. Let's obj dump it. And now if we look at bar, we see that bar calls puts, and then it calls exit, and we're screwed, right? If we jump here, we will get our leak, but then the program will exit. So let's just get that first, and then we'll talk about what to leak and how to leak it and survive with the program. All right, so we're going to jump right here to the thing that calls puts and see what happens. Okay. Back up. Sorry. All right. The baby is in good hands. All right. So we jump straight to the puts, and then things crash. Why do they crash? Let's find out. The awesome thing about computers is you can always understand what's going on. So we can pwn.gdb.attach to p, and then continue. And here we crashed in strlen. Of course, what does puts do? Puts will take the strlen of the argument and then write that much and then write a new line. Super simple. Let's see where we crashed. We crashed at some insane instruction, but it's an instruction that did a pointer dereference into RDI, the first argument. And let's see what RDI is. RDI was null, so we got kind of screwed, right? And we can actually confirm what is going on by doing this again. And actually, I recently found out that you can put in commands here to automatically run. So we're just going to be super awesome. So our call puts adder is here. And we'll do call puts adder. And here we'll break at hex call puts adder. And continue immediately. Okay. Oh, no. It's here. Yeah. Okay, perfect. Oh, we can't do that? We can't have a semicolon? Ah, I know why. Hold on. Can we have a new line? Awesome. Okay. So, we launched GDB, attached to it, and immediately put a breakpoint at the right address and did a continue. This is a nice hack to, you know, just very easily break at the right spot instead of having to figure out, you know, every time rerun the same breakpoint commands and so forth. Here we are. We're at this breakpoint. Let's see what RDI is. Yep. Right as we're about to call puts, RDI is 0. But that's okay. We can set RDI because we have in our gadget list pop RDI ret, which is super nice. And it's actually super common, right? All right, so we're going to copy that address. Let's quit out of this. Take this. Okay, so basically we're keeping a list of gadget addresses. Okay. And we have pop RDI is this. Okay. So let's actually first, I'm going to make this a multi-line thing with comments for your benefit. So here, this is the buffer. This is saved RBP. And now our ROP chain begins. So we'll put in the pop RDI. And pop RDI needs a, of course, we need an RDI to pop that will also go on the stack. So let's just put in 41, 41, 41, 4. Let's do 41, 42, 43, 44, 45, 46, 47, 48. So obviously this is not a valid pointer, but that's what will get popped into RDI, and then puts will run. Okay, so now we run this. All right, here we are in the breakpoint. We're about to execute this instruction, and in RDI we have 41, 42. Awesome, right? So now let's leak something. So what can we print? What do we know addresses of? Do we know anything on the stack? No, the stack is randomized every time we run. Do we know anything on in libraries? No, that's randomized every time we run. The only addresses we know are in the binary itself. That is always at this 40000. Let's just print out the very beginning of the binary. This should be 7F ELF, our ELF header, right? We're very used to seeing that ELF header from our various other assignments and the fundamentals lecture. So what we're going to put here is just the base of the binary. We're going to continue, and it exited with code 1, which makes sense because if we cat rop example.c, we did an exit 1. Okay, and before exiting, it printed 7F ELF blah 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 blah. So boom. The program was never supposed to be to print us anything. It was just did the overflow and crash, but we redirected it to the print. And now, using ROP, we actually set RDI. We're building the Lego masterpiece. Okay, awesome. So now what? Now we have two problems. One is that print is not really useful. 7F ELF. We know that that's what the program starts with. That's the standard elf header. And then, of course, the second problem is that exit. Even if we had leaked something useful, the program immediately dies. That's not fun. All right, so let's figure out how we're going to make this work. And to do that, let's see what happens when you call puts, right? If you notice, let's actually rerun this. If you notice, we are at this call into our binary, but it's saying puts, right? Puts is a libc function. Like read, etc., etc. Of course, there's the read system call, the read libc function. The read libc function calls the read system call eventually. If we actually disassemble, okay, we'll get into that later. But basically, puts is not a function in our binary. Puts is a function in our libc. But here we're jumping to this to our binary. And we're specifically jumping to this weird puts at PLT location. And what the hell is that? Let's step into it and find out. So now we're in this puts at PLT. And we do some really weird thing here. Ignore this. But what we do... Of course, now you should be able to recognize this end BR64 instruction. That's great. It's a valid jump target, of course. PLT is the procedure linkage table. It has a bunch of launch points from code that code in your library uses to run code in the code in your binary uses to run code in libraries. What this does is performs an indirect jump. It looks up inside the binary at this offset from the instruction pointer. So the instruction pointer here is at 401064, and this adds hexadecimal 2FAD. So it'll read 403F something something, right? And if you look at our dump here, is 403 something something something, and that is mapped in memory, readable by this program. And what is it? This is called a GOT entry. So let's step here. So now RIP is right there. We can read it. We're one off, I think, because of... No. There we go. Yeah, we're this still doesn't look... We're two off because of the way... Yes. Okay, perfect. We're... because of the way that... But when this program runs, RIP will be pointing at the next instruction, if you remember. But the bottom line is, this will read a value that is stored somewhere in your program. And this value... nope, it was only 2 off. Why is it only 2 off? All right, we're not going to investigate, but this value here... No, hold on. That's 3. Minus 1. Oh, it's only 1 off. Why is it 1 off? Some weird GDB thing, probably. This value here is a valid pointer, and specifically, it points to the NBR. It's a valid jump target. If we step, we are now... Why is this resolver running? let's restart this to avoid confusion, more confusion than necessary. All right. Here we are. Okay. When this runs, RIP should be this value. So let's see what this plus this is. There we go. Okay. Puts at PLT jumps to puts at jumps to a register a pointer, jumps to a value stored at a location called puts at got.plt. What happens is this. Let's pull up Binary Ninja doesn't have a very good UI for this, does it? Kind of does. All right. This binary imports a couple of things. One of these things is puts, right? Puts, this is that NBR64. Binary Ninja doesn't support it yet. And this is that jump. If you double click here, there is data in another section in memory that basically contains a bunch of libc addresses. And it is initialized. I'm a little disappointed in this because it's supposed to be, I wonder if GDB disables this. You'll notice this isn't a libc address. But if we step through and we see what is actually going on, it pushes some value 0, then it jumps into another part of our binary. This is all dynamic resolver code. This does some crazy stuff, and then in the end we end up in the library, in the LD library, right? This is the dynamic loader, which will figure out where puts is in libc and jump there. But after it does so, let's just finish this. So if we're back in bar, we just called puts. If we see the value of puts in the GOT now, it has been resolved to its actual location in libc. Bottom line is there are multiple ways to call puts. If we know its location in libc, we call it. If we don't know the location in libc, we can actually call what is called the PLT stub, this code that will look up its location and jump there. Super cool. All right. This means that we can avoid having the program exit on us by figuring out where the PLT entry is and jumping there. So this binary uses 3 functions from libc: puts, read, and exit. We can jump to puts here, and now we avoid that exit call that is right after the normal way the binary calls puts. So say here is puts PLT, and then we just say, instead of at call puts, let's actually not break anywhere. Actually, let's give it a continue without the break. Okay. So here we'll do puts PLT. Actually, let's not attach that at all. We run it. Boom. Still works. And now it didn't exit. In fact, it segfaulted. It returned signal 11, right? Why did it segfault? Because it kept running and started, return to some garbage that was previously on the stack and probably crashed. We can make it, of course, return cleanly. We can pop RDI into whatever. What do we want to return? Value 42, and then we can figure out where the exit PLT is. So exit PLT is here, 401080. And by the way, successive PLT entries are usually hex 20 apart, 32 bytes each, aligned that way. And then we call exit. So now we're building a little program, right? First we load up, it's for 1000, the beginning of the binary. Then we print it out. Then we load 42 into RDI, and then we exit. We call exit. So now we run this. It doesn't work because we didn't put a plus here. Boom. Now it exited with exit code 42. We're controlling this binary. This is incredible. Okay. Let's add some comments for those watching later. So this is load a pointer into RDI, call puts to print the data at that pointer, load a return code for exit, exit with that return code. Amazing. Okay, so this is all very great, but it doesn't get us quite there yet to getting the flag. First of all, we want to print out something useful, right? If you recall, when puts runs, the address of puts in libc gets put into the GOT entry of puts, right? So, excuse me, let's look up where that GOT entry is and print that out, and that'll give us the address of puts in libc. So here is the indirect jump. Of course, RIP is always pointing to the next instruction, so that's going to be this instruction plus 2FAD. So we can do puts GOT equals this instruction plus 2FAD. And instead of leaking out the beginning of the binary, we leak out puts GOT. That looks like an address. So, question on ROP. Where did 40106B come from again? What is 40106? Oh, it's the puts GOT. Okay, yes, the 40106B. So we looked at the puts PLT. In the puts PLT entry, right here, we do an indirect jump. And the indirect jump reads a pointer from RIP plus OX2FAD. RIP is our return, our instruction pointer, right? RIP, whenever you're executing an x86 instruction, like Yan85 actually, RIP is always pointing to the next instruction. It makes it easier that way for the CPU to just fetch the next instruction when it needs to. So RIP is pointing to this 4016B, which is the next instruction. That's where 4016B came from. That's why we have 4016B, and this is that offset for the RIP relative read, and that's where the GOT is. And now we've leaked it. We also leaked a new line, right? Because puts will print a new line. So we say puts libc, so libc puts adder is r.readline minus the new line, and then of course let's unpack this into an integer so we can do, you know, plus and minus and stuff on it. There's no r, it's p. Okay, int object has no attribute in code. Oops. Oh, first, for one thing, how big is this? This isn't going to be a full 8 bytes, right? because oh, oops, there should be colon -1. Okay, that's what happened. All right. Didn't print that. It's 6 bytes long. Why is it 6 bytes long? If you look at these addresses, they're all basically 1 byte, 2 bytes, 3 bytes, 4 bytes, 5 bytes, 6 bytes. And then the most significant 2 bytes are all nulls. So when we use puts, it'll of course stop printing. It's a string operation. It'll start printing on the null. And then we're screwed. So, or not screwed. We know the rest are nulls. So we can just add them. 2 null bytes. And then we can unpack these into an address and print out that address in hexadecimal. Boom! We have the address of puts in libc. And we can see that successive runs, it changes. It went from 7F98, 7F0B. Very cool. One problem. We ran it, we leaked it, we know where puts is in libc, and thus, because we have libc, it's locally, it's in user, whatever, lib, blah, blah, blah. Because of this, we know where everything is in libc. And we know where all of those sweet, sweet gadgets are. The huge amount of gadgets in libc. All of these beautiful gadgets, that there's so many that RP++ takes some time to even find them, are available to us. Several problems. One is we know that where those gadgets are after we send our ROP chain. Uh-oh. 2, the program's dead, so we can't send another ROP chain. But we control the program. Program doesn't die until we tell it that it can. That turned out kind of morbid. But we build the Lego set. Lego set's not done until we say so. All right. Can I show the RP++ command? There you go. It's also in the slides. It's also in module, or in the third lecture of the module. Okay. So, there's a question. How do you see what version of libc a library is using? For remote exploitation, this is an art. Right now, we're talking about cases where you are on the machine and you're exploiting /babyrop, whatever. You can do LDD, the binary, to see which libraries it will load, and there it is, the exact file. Okay, so now we need to understand 2 things. One, how the hell can we get control again after this? Because the program's about to quit, right? So that's not good. And 2, how to actually use these libc addresses. Now, that's fine. We can do that. We'll do that one step at a time. First, let's get back to a point where we can do the send another ROP chain, for example, or do something else. And we can. For example, if we look here at interesting functionality already in the application, there's a program that is very nice because it has a stack-based overflow and then returns. Why don't we just run this program again? Why not? Let's just jump here, back to main, and everything will be magically good. I need to copy properly. Okay, so we will add, let's add another gadget address here. Okay, let's try this. What happens? Boom, it's not returning. Why is it not returning? Very simple. Because it's called main, it has called main, and it's waiting for more input from us. How awesome is that? Right, so now we have gone from, we have still figured out where libc is, and we've looped the program again to re-trigger the vulnerability. It's not always so easy. Most of the time, programs will do stuff with their arguments. Oftentimes, if you have fucked up this If you've messed up the stack, actually dereferencing these arguments is going to be disastrous. But I have faith that you can figure out how to make it not crash and keep running. Okay. Cool. So, let's kill this. So now, over here, program is ready for ROP stage 2. Okay, so now we can build a second ROP chain. What should we do? Let's start out making it exit cleanly, just to make sure that we have everything, all our ducks in a row. Do 42 again. Boom, it works! Exit code 42. How cool is that? All right, now, a couple of things. We have the puts address in libc. Now, we can, of course, have the program, we can call the puts address directly. So here, we're going to print out the, just for fun again, the base address of the binary. So this is the 7FELF, but we're going to use libc's puts address and make sure that this works. And it does. This is incredible. We have full, basically we're, at this point we're almost done. And it looks like we might be able to finish in time for a nice solid hour of collaboration, but we'll leave the collaboration room, as I said, open all week, so don't panic. Okay, so then what do we want to do here? Well, what we want to do here really is either drop a shell or do any of a number of other things. Some action that will get us the flag eventually. So what we are going to do here is something like, let's just call well, let's call sleep to begin with, just to show you that we have full control, and then later we can do other crazy stuff. So there's a question on Twitch. Can you use a shell to get the flag? Because execve drops privileges. Execve does not drop privileges. binsh drops privileges when it's run. Execve is perfectly happy maintaining the privileges that it always had. And I'll actually show you how to work around binsh dropping privileges right now. binsh drops privileges, if you recall the baby suid module, when the effective user ID is 0, but the saved user ID or the real user ID, I forget which one, but we'll set both of them, is non-zero. But the nice thing, when you have an effective user ID of 0, which you do when you're running these set UID binaries, you can actually set your other user IDs, your saved and real user ID to 0 perfectly fine. Okay. There's another question. What if the addresses are PIE? Well, then you are in a little bit of trouble. I'll mention that after we solve this base case. Okay. So, what do we have? What do we want to do? Let's start with sleep, right? Let's call sleep with a large, or like with 5, and then just prove to ourselves that we can call arbitrary things. In order to do that, we need to figure out where sleep is. We know where puts is. We know what libc is because we have that file. So we can figure out where sleep is. If you do LDD, let's look at all of these symbols in this binary using NM. Graph for put. There, okay. Puts is at 875A0 into libc, and this actually makes sense. If you look at this address, it said something 5A0. So that last 3 nibbles are exactly where we expect them to be. So we can libc base adder is libc puts adder minus the offset of puts. Amazing. Now let's remove that. Now let's actually practice printing out the libc elf header. right? Just for fun, just to make sure we have it right. libc base adder from the libc puts adder. Okay, we run it. Woo! 7 FELF, what a rush. Okay, awesome. So now we are printing out the libc base adder. Now we have puts, of course, we can calculate arbitrary things. You want to call sleep? Boom, call sleep. Here it is, E5F40. We can call anything. Libc sleep adder is this. So let's actually sleep for, so let's comment this out. We don't want to do that. Now we want to sleep for 5 seconds. Okay, we load 5 into our DI, and we sleep. libc sleep adder, run, it crashed. Oh, oops. Yeah, add base to sleep, and I guess the Greek coffee kicked in. Yes, so libc sleep adder is libc base adder plus whatever. 5, 4, 3, 2, 1. Boom. We slept. We can run arbitrary code in libc. How awesome is that? Very awesome. It's very awesome. Okay. So, now what? Now we face a challenge, right? We need to read the flag. To do that, there's a number of ways. We can open send file, open read write. That one's a little tougher because you need to know what address to write to, but that's okay. We can leak out arbitrary values now. We find a gadget that will load our stack address into RAX, which they're everywhere, because libc basically fundamentally gives us unlimited gadgets. So if we grab RAX, grab RSP, move RSI RSP. It's let's do this. Grab RAX RSP. Okay, that's dangerous. Yeah, so we can, is there one that ends in a ret? All right, we're going off a little bit on a tangent here. Let's see things that'll push RSP. This will return to our stack. Okay, so we still don't have an easy way to get from RSP into RAX, but I'm sure this exists and we can do it here by abusing libc, but that's overcomplicating things anyways. We already have arbitrary execution now. All we really need to do is open /flag and send file. And for send file, of course, we need to run a bunch of set a bunch of registers. So it's send file 0, and then that file descriptor, usually 3, 0, and 1000. Okay. Or someone says we can chmod. So here we'll want to chmod /flag. All right, let's try it. Instead of sleeping for 5 seconds, we're going to chmod the flag to read it out. How will we do that? Well, one, of course, we can call chmod. That is easy. Let's figure out where it is. Chmod is at 110 CD0. Okay, so calling chmod is easy, and we need a pop RDI, pop RSI gadget, but if we have libc, there's for sure a way to set RSI. That's RSI is going to be the second argument, the actual permissions that we want to chmod to. There we go. There's 182 pop RSI gadgets in libc. This is the base address of the, or the offset. So libc pop RSI is here. Okay, amazing. So now we want to do libc pop RSI, and we want to make it 444. It's root readable, or owner readable, group readable, world readable. This last 4 is really the important thing. Let's just make it 004. Why not? World readable and root user and group can't read it, or donor and the group can't read it. Okay, this is still a little tricky. For now, let's set it to 41, 42, 43, 44, 45, 46, 47, 48, because that's cool. All right, so we're about to call chmod on garbage pointer and 004 in octal, which is 4. Okay, we run it, exit code 42. Let's GDB this. Now we're going to debug. We're going to actually break at libc chmod adder and see what's going on. Okay. Why didn't it work? Oh, oops. Hold on. This should be a format string. There. Okay, so we're going to break at libc chmod adder. Here we go. It triggered it. RDI, bummer, and RSI, 4. Amazing. So RDI, that's not a bummer. That's what we set it to. We have a, you know, it's correct. That will have to eventually, because if you do man chmod, the call to chmod takes path name and the mode. Of course, it can also take a file descriptor. We can open /flag and then fchmod, just a different function. The problem is we still need the file name, so we might as well just chmod. Okay, so that the file name is still problematic, but we have this 4. Why didn't it crash if this is pointing to a random unmapped memory? Well, let's take a look. Oops. Let's take a look at chmod. Chmod, like I said, the library function is a thin wrap around the syscall. So it'll actually call the chmod syscall. The chmod syscall, here we are. We're about to execute the syscall. What's RAX right now? Some random value. The syscall return value in RAX is negative something. That negative something is actually E in val. Return value. E in val means, no, not E in val. E mem. E no mem. Nope. E fault. Path name points outside your accessible address space. Boom. That's my guess on what that is, because we passed into the system call unmapped memory. System calls never segfault. If we had accessed that memory in any way in libc, we'd cause a segfault. But the system call lets us survive that. Okay. Oh, oops. Someone mentioned. Oh no, I did. Oh, not OX. Yeah. Okay. Cool. All right. So, and then of course we exit with code 42. So now we have one remaining problem, and that is to put /flag here. How the heck are we going to do that? That's going to be painful, right? We can of course input /flag onto the stack using this overflow, but where is the stack? We'll need to get an address to the stack here, and we could do that. We could find the gadgets. I'm positive, but we can do something a little simpler. Let's take a look at all of the addresses that we know about that are writable, and the easiest one is back here in the main binary, which is position dependent. There is an entire page of writable memory. This is the page containing the BSS, global variables, and the dot data, global variables that should be able to be updated and so forth. So let's just write here. So we are going to build using a using ROP the word /flag in memory. So let's take a look. What do we need for that? We need a instruction that will move something keyword. Okay, because we're going to do /flag null null null. So here it writes, this guy looks perfect, right? Move keyword R9 RCX and then a ret. All right, so that looks pretty good. What else? Move keyword RBX and RDI, but then a call. So we can actually filter this down even more. So we say, give us a word here. These are regular expressions. I highly recommend you learn regular expressions in your in the process of your education. Here's another word, and then a semicolon, and then a ret. Okay, and then actually let's say this is where we will start. Oops. Why didn't that work? Is this a tab? How about just a bunch of spaces? Okay, I don't know why that didn't work. Okay, let's make -R1 instead of -R2 to reduce this. There we go. All right, these are all the ways that we can write memory, right? If we can set RAX and RDI, guarantee you we can do that. We're golden. We can write memory. All right, so how do we do that? Let's grep move RAX. Or sorry, not move RAX, pop RAX. Boom, pop RAX ret. libc pop RAX. C base adder plus. Oops. Whoa, what's going on? My code. Okay, it's back. This guy. Okay. Perfect. And then let's do pop. What was it? We decided pop RAX and fuck. RAX and RDI. So let's do this. And we already have the pop RDI gadget in the main library. And here is libc move. Let's see. Libc write RDI to RAX, right? RDI to RAX. As this guy is libc base adder plus boom. Cool. Okay, so then we have we need to set RAX, set RDI. So we're going to set RAX to that writable page. That's right here. 404,000, and that for us is known because there's no position independence. But at this point, even if there was, we now have very strong capabilities because we know where libc is. If you see in libc, there are also writable pages, right? It's just a longer address. So let's just use this. Okay. So now we write that into RAX. We're going to write /flag into RDI. Okay. Perfect. And that should be 8 by 1, 2, 3, 4, 5, 6, 7, 8. Perfect. And then this is libc pop RAX, right? This is in the main binary. And this is write RDI to RAX. Okay, perfect. And then we will return from there to setting RDI back to this value. And then we'll call chown. Amazing. Amazing. Okay. Boom. What's going on? It crashed. Okay. Something's wrong. Something's wrong in our code, that is, which is better than something being wrong in our exploit. These weren't bytes. We put this as a string. Man, worst thing Python 3 ever did was mess up the beautiful, beautiful strings. Write RDI to RAX. It's libc write RDI to RAX. Let's kill this. Okay. Okay. chmod. RDI is right what we thought it was. And it's /flag. And RSI is still what we want. Continue. And we exit it cleanly. Let's actually remove the GDB. Boom. Exit cleanly. Oh, my binary isn't set UID. So hold on. Let me do this whole thing. chmod 600/flag. Okay. chmod 4755. ROP example. Hold on. Root.root. ROP example. And there we go. Now it's set UID. Now we run it. The flag is now readable. Awesome. Awesome. All right. So this is our not our first ROP, our second ROP. This is complicated. It is a leak. But let's take a look at everything here. We use puts to leak the libc base address, or the libc puts address, which tells us everything we need to know about libc, which then gives us a my mind just went blank, which then gives us the which then allows us to ROP through libc. But in order to do that, we need to loop the binary back around. We jump back into main. Of course, we got lucky here. Main had no requirements. It runs in a vacuum, right? If main starts accessing environment and stuff, you need to make sure the arguments are set up properly. And then we had our second stage ROP payload, which set up /flag in memory and ran chmod, which made the flag world writable. And then, to make sure nothing crashed, everything worked properly, and then we exited cleanly like a polite guest. We cleaned up our Legos. Cool. All right. This is how you ROP. We also covered the GOT. That's very important. That allows you to get a leak. So there was a question: what if this was this thing was PIE? It would be tough. Remember baby mem. You exploited a PIE binary by overflowing just the last couple of just the final byte or two, the least significant byte or two of the return address. Because of little endian, that the first 2 bytes you overflow are the least significant bytes, right? So this lets you reposition execution a little bit without even knowing the base address. Using that and being careful where you jump to, you can often cause a, and you will need to, in the assignment, cause a leak to happen and then loop the program again, of course. Okay. But for sure, if your code, your main binary is position dependent, which is increasingly becoming the case, then this becomes harder. A lot of the challenges in this module actually gift you a stack leak. Okay, so now what? I want to cover one more topic. In the lectures, I mentioned stack pivoting, right? Stack pivoting is when you say, okay, I know that there's some other place where I can write data to, right? For example, in our example, this page, you know where it is, and it's writable. And let's say that you can write data to it. Say I can write a lot of data, but I can only overflow the return address by a very little bit. Let's say two gadgets or something. So that's not enough to carry out a full attack. Our attack here was, stage 1 was 3 gadgets with one of the gadgets having an argument, and stage 2 was 1, 2, 3, 4, 5, 6 gadgets, even including our nice exit, most of them having arguments, right? So that's quite a lot. If you're limited in what you can actually run, then you won't have enough. So how do you handle that? You can handle that by pivoting your stack. If there's another place in the binary that you know the location of, you can set RSP to that location. And suddenly, the only thing that makes your stack is that RSP points to it. And suddenly you're golden. Of course, you have to be careful. If you call into libc and libc starts setting up stuff on the stack, it might run out of room. So you have to align it properly. You might actually have to, and remember the stack grows to the left, so you might have to point to the rightmost part of this address, of that page, but that's fine. How do you pivot the stack, right? There are a couple ways. One is, if you know where libc is, obviously it becomes much easier because there's tons of gadgets. But by the time you know where libc is, you often don't have to anymore, because there's also syscall in libc. You can just write shellcode that executes syscall directly. It's super easy. Okay, but what else can you do? You can my mind went blank. For example, exchange RAX RSP for whatever reason. Exchange RSP with something. What? Interesting. I thought this was more common than maybe. An interesting thing with ROP is as time goes on, fewer and fewer good gadgets are available. There's still plenty in libc to get what you need done, but there is a bit of a thought to reducing the amount of gadgets available. I realized what happened. I lowered them to make it harder for attackers. All right. Here is exchange RAX with RSP, for example. The moment you do this, the rest of the gadget's irrelevant because... Oh, no, it's not. What am I doing? The moment it returns, the rest of the gadget is irrelevant. So, is that the only exchange gadget? Did they really take it out? What? R2. Yeah. There's no... Okay. That's out. Here's a good way to pivot the stack. Pop RSP ret. If you can find a gadget like that, pop RSP overwrites your stack pointer with whatever argument you send next on the stack, and then when you do the ret, you're now returning to, you're reading the return address from your new stack and the rest of the payload on your new stack. This gadget exists in libc, but it doesn't exist in your original binary. No way. No way. So what does exist? Let's take this R2. Very few things. If you grep for RSP at all, the only things explicitly messing with RSP are these stack shifting gadgets. That's not very good. That's not enough to do a pivot. There is one instruction that is extremely common that has an impact on RSP, and that is leave. What is leave? Leave is an instruction that basically performs two things. Leave is the same as saying move RSP RBP, pop RBP. That's leave. It's just those two instructions in one. This overwrites RSP with RBP. Normally RBP is your base pointer. But you can, of course, set RBP anywhere else. Pop RBP ret, for example. This is a common gadget. So by combining these two, by setting RBP and then by using a leave, you can shift your stack anywhere you want. All right. I think those are all the concepts now. Let me take a look at my notes. Uh-oh. Okay, there are my notes. Yep. Awesome. Those are all the concepts I needed to convey. Yeah, so on the Twitch chat, people are discussing 2.31 is hard to ROP in. It is. Things are getting harder. As I mentioned in the fourth video of ROP, Intel just released new processors that will almost completely kill this sort of fine-grained ROP that we're talking about. In a couple of years, we'll have to adapt. ROP will become harder. It'll still be possible, but it'll be quite a lot harder. All right, there's a question on Zoom. Will we have SIGROP on this homework? No, we won't have SIGROP. It's a very situational thing, and it's an advanced ROP technique, but we're going to do it, or we're not going to do SIGROP in this module. All right. There's an RPI sec individual that is advertising Hack the Vote this weekend. It's the CTF at the beginning of class. I mentioned from my alma mater. You can practice a lot of these concepts. You should play. A question on Twitch. Are you the professor of an online class? Yes, I am. When COVID isn't raging, I'm also the professor of an offline class. Let me put in the site for the there we go. This is the website of the class. It's a class at Arizona State University, but it's open to everyone this year, obviously. You can actually go and do the practice problems. On that note, Connor, are we good with the practice problems? Let's launch. Uh-oh. Hold on, Connor. By accident, people heard your voice. Yeah, it has to be okay because I can't redirect audio. Why is that? Hold on. We're going to... Connor, say something. Yeah, I can hear you. Okay, perfect. Okay, good. That's... All right. How many... we launched 6 or 8? Okay. So, 6 ROP challenges are live. Today, we have a special set of guest challenges from the captain of the Pwn Devils. Someone's saying, Connor, in the Twitch, on Baby ROP, no level 1. So level 1 exists, but it's just not in order. So it's there. We'll try to figure out why it's not in order. Okay. So you can, of course, do challenges out of order, but I would recommend starting with level 1. These levels are going to walk you through the concepts really step by step, and a lot of the tough as nails ones were created by the captain of the Pwn Devils, Mahalos. He's on Twitch. Say hi. He runs the Pwn Devils club at ASU, and then he's a core member of Shellfish, one of the, as I often say, oldest and coolest hacking teams in the world, but they're my old team. I'm actually a captain emeritus. I'm passed on the torch, and one of the new dynamic people is Mahalos. Another one is Connor, who's always talking in my ear. Another one is Will. You know him from the level 14 walkthrough. His handle is Clam. His handle is Classum. So we have a minor disaster reported. What's the minor disaster? Oh no. How? Okay. Teaching is currently broken. All the teaching levels. All the teaching levels? Okay. Oh, I see. Yes. So the teaching challenges are currently broken because of our disassembly helper. Connor's going to fix that real quick. In the meantime, go for the testing challenges. Okay, so challenges are up. We're going to launch 6 more tomorrow at midnight. These first six should help get you... actually, we're going to launch 2 more tonight, and then... Wait, Connor, how many more are we going to launch tonight? We're going to launch at least 2 more tonight, and we're going to launch at least... So we're going to 2 to 4 tonight, and then 2 more tomorrow for a total of 12 levels of challenges. It's going to be awesome. This is an exciting module. You're just playing Legos. That's what you're doing in lots of different things. It'll be awesome. Let's open the collab rooms. Oh, they're already open. They were never closed. Everyone pile into the collaboration. Yes. What's the question? So the question is, if you want to leak a libc address, do you usually have to find a PLT stub within the binary? Honestly, it's very situational depending on the vulnerability. The PLT stubs are a good source of addresses, but oftentimes the binary itself is PIE, right? And so first you need to read the binary address. There are a lot of addresses on the stack, whether as explicit return addresses or just leftover, right? So in the baby BEM and toddler modules, you've taken advantage of leftover stuff on the stack to leak addresses. You can do the same thing depending on the vulnerability. In most levels here, you will be given an address that you need. Sometimes you will have to get it out by using functionality in the binary. But yeah, the PLT is a good target. Other targets on the stack. Okay, so things in the PLT. Sometimes things oftentimes like STD in and STD out, those things are imported as well. So there are pointers in the various in that RO data and that data. But the GOT is the kind of big one, and then on the stack. Okay. Then there's a question. Are you going to walk through one level? Without teaching mode, do you think I can do it? I will try. All right. Let's go to... So collaboration is up. We have... Come on. We have 2 people in collaboration. See, this is the problem. With the collaboration not squeezed into 1 hour, people aren't collaborating. Pile in. Collaborate away. Go, go, go. All right, now we have 3 people in different... 4 people. Awesome, but all in different rooms. So we have room Swarm, Trade, Tracker, and Trust. Okay. Flynn says testing 1 easy. I'm going to try testing 1. Let's do it. I don't know if you can hear Baby Yan. She's babbling in the background. Very happy now that she's not... Uh-oh. Oh, no, okay. What? Wow, it's really out of order. Okay. Let's launch. I think Baby Yan had... stage fright. Okay. What have you got? Level 1. Testing 1. Let's look at main. Welcome to main. It reads an enormous amount of data to RSI. RSI comes from RAX. RAX comes from var48. No, is the address of var48, so it's RBP minus hex 80. When we stream hex 1000 over that, obviously we destroy the stack, and then it returns. So, very cool stuff. You'll notice right away this has a win function that gives us the flag. So how do you do it? You actually done this level before in the memory corruption. We're just connecting the concepts. So all we do is take this and wrap all the way in here. Let's launch this up. Okay. We're back to /B tab. Some people would be happy. So let's send this. Oh, thank you for letting me know. All right. So this should be super easy. We just send this times, I don't know, 16 times. And then see what happens. How did it not crash? Let's do clean instead. Boom. We triggered win probably 13 times or so because part of this was used as the overflow itself. And then here's my flag. Don't steal this flag. You'll be flagged for cheating. Get your own flag. Okay. One thing I just did. I did this sled. I just said, call win 16 times. I don't care. But realistically, you need to be careful in your ROP chain. Similar to being careful in your shellcode. If you, except for that final syscall that calls send file, which win basically is the equivalent of, you can't just spam gadgets or spam instructions unless they are just rets. So if I find a gadget that is just ret, which always exists obviously, unless you're in some exotic challenge, but it always exists. I can create a sled using just rets, a ret sled instead of a nop sled. Whatever, times 20, and then this once, and we're golden. Right? Don't underestimate ret sleds in making your life a little easier. Typically, you actually need them a little less frequently than you need a nop sled. The stack tends to be more stable offset-wise, relatively speaking, but it's useful every once in a while, especially when you're stack pivoting. Pivoting into a ret sled, it's a little less precision needed. Okay, Connor has updated. Teaching is now working. I'm going to show you one awesome functionality. Really proud of this in teaching. Let's launch up level 1 teaching. We run this challenge. So if we run, oops. Oh no, it didn't save my stuff. Okay. If we run stuff to override the return address, Connor, I think we introduced a bug here. Oh, again? It's not actually disassembling the wrap chain. Oh, no, you're right. I didn't put in enough bytes. I needed at least 112. Thank you. All right. So similar to the shellcoding module, and some of the toddler levels, we're going to do all we can to give you the tools you need. But those tools are also GDB. So you can do the same thing on the testing modules with GDB, but we'll actually go through and we'll dump your wrap chain for you before executing it. If we this is not testing one anymore. Obviously, these addresses won't make any sense, but that's okay. If we print this out, are you sure you fixed it? All right, Connor's going to look into why this looks like shit. But it didn't look like shit last night when we tested all of this, but we'll figure it out. But this will have the wrap gadgets, but you can get the same effect with GDB. You can break at that final return and just go through and look at all of your disassemble everything that your stack points to. Cool. Okay, let's see. Do we have collaboration going on? All right, we have 5 people in room trust. Oof, you're bringing this onto yourselves. All right, we're going to try to have collaboration hours scheduled 6 p.m. every day. We're not going to do anything special for that on stream. It is just not feasible with our schedules. But hopefully it'll encourage everyone to pile in at 6 p.m. Collaboration, as someone said on Twitch, works best when you mention specific questions. Yeah. The Twitch chat, the 5 people collaborating are the whole 5 people left in the class. Maybe. One day we'll figure out how to keep the drop rate lower. I think the solution is better early stage preparation and earlier parts of your curriculums. Cool. All right. Any questions from the crowd? Let's see how. No one solved teaching 1 yet. Let's refresh. Okay. 23 solves. Awesome on the first ROP. 8 solves on teaching. Only time in history where teaching is easier. Okay. Level 2 already 2 solves. 4 solves on testing. Level 3 remains unsolved. Awesome. I'm excited. I'm excited who will truly master ROPing. Omega Valkyrion. Yeah. Question was, most of the challenges are not PIE. I think that's accurate in terms of raw numbers, yes. Yeah. Okay. The question was, can we get an example of how to deal with PIE challenges? Let me just get you a start. Okay, let me restart this and run that. We'll just save off that history. Okay, perfect. Let's change ROP example.c. Or rather, let's change how it's compiled to make it PIE. Okay. Now, of course, we'll do ROP example. We cat the maps. It's in some random place, and that place will change every time. What is stable is the last, 3 nibbles of the address. Okay, cool. So Mahalos, who again wrote a big chunk of this these challenges, he told me to tell you. I don't remember if I actually got around to telling this. He wrote all the good ones. Connor wrote all the okay ones. I wrote the terrible ones, obviously. Yeah, you can figure out how much you suffered on a level, and then you probably know who wrote what. They're much nicer than I am. Anyways, all right. So the last byte is stable. So if you override the last byte of a return address, you will jump somewhere in that return address. So I'm just going to show you an example of how to loop this binary, at least, right? So let's start over here and go back to stage 1. Here we don't no longer know where anything is. And in fact, that binary that I just wrote is not solvable. We need some extra capability. So we get just a little bit of something. So let's just say let's crash at 4.1, 4.2, 4.3, 4.4, 4.5, 4.6, 4.7, 4.8, and print p.readall, print p.poll. Sec faults, if we attach with a debugger, it's sec faulted, and it's sec faulted because it was about to return to random memory. Okay. Let's say we want to, obviously, if we don't overflow anything, if we just fill enough for the buffer, it exits normally. I forgot to disable GDB here. exit code 0. Okay. So, what to put here? Well, what to put here to loop the binary is obviously the address of main. We don't know the address of main, but we know the last byte. Actually, we have a problem. Let's change it a little bit, and then I'll let you generalize that. Let's say main runs vuln, and vuln has the vulnerability. Two problems. 1, 2. Okay. Oops. Okay. Main runs vuln. Vuln has the vulnerability. Why is this important? Because, of course, now in vuln's stack frame is the return address of main at the end of main, and we're going to change it. Let's just take a look. We'll break. Actually, we just won't continue. Okay. So here we are. We are in the read syscall, or in the read syscall wrapper. We step until we're back in vuln. We're gonna, by the time we return in RSP, there's all this garbage. Let's disable that overwrite. Quit our old instances of GDB. Disable that overwrite. Actually, let's disable this too. Okay. Okay, we return from read. When we're about to return from vuln, we have some address. If we look at what that is some address in main at C5. What about main? Main is at B3. What about vuln? Vuln is at 8-9. And it's not the end of the world if this nibble is different too. Then we can overwrite the top 2 bytes. Likely you'll crash 1 out of 16 times because you'll overwrite that top nibble with something incorrect, or you'll trigger some bizarre behavior somewhere. But you just try it 16 times. It'll work one of those times, statistically speaking. But in this case, we don't even have to do that. We can just overwrite 1 byte with 89. Right? So that's what we'll do. We have the buffer. We have our RDP that we overwrite, and then hex 89. Continue. And we're hung. Why are we hung? We're hung because we're back in the read again. We looped the program, even though it's PIE. But that's all we can do in this case, right? Because, again, it's PIE. Now, in our case, we were kind of screwed because my mind's going blank. The Greek coffee's wearing off. We're screwed because main is so simple, or vuln is so simple. If vuln did this, now we're in business. We jump back into code that executes both of these using our ability to control the stack, and this will cause, if we are careful enough, we can reuse this puts to leak out some address, and then this read will run immediately afterwards. Cool. Okay. All right. What else? We have 5 minutes left in the class time. Now we're up to 1, 2, 3, 4, 5, 6, 7 people collaborating. Awesome. Should get that up more. More collaboration. Okay, there's a request. Repeat the summary of what I did to loop this code. Basically, I realized that if I don't send anything, if I don't overflow, and I break at this return, let's just see where that is. We break at the return from vuln. Oh, we don't know where that is because it's PIE. Okay, that's fine. We'll just attach and walk through. What? Oh, we did attach twice. Okay, we attach. Okay. The old return address, if he didn't overflow anything. Oh, oops, RSP goes into main. Right? That makes sense. This is main plus 18. Main plus 18 is it's right after this call. It's where the call will return to, right? And you can see 11B3 plus 18 is exactly this 11C5. And you can see the address here ends in 1C5. It's right after. The easier way to do it is this XI. This move EAX0 right here. Okay, so what does this allow you to do? This means that if you just overwrite the last byte, you can reposition control flow, redirect control flow within the binary. You did this in BabyMem. So go back to BabyMem. It's a very similar challenge, but this has it's extra because it doesn't have a win function, right? So you did this in BabyMem, and the way that we do this is just overflow it with 1 byte, and that 1 byte is where we want to go. This redirects it. It's the last byte of vuln 89 instead of C5. So instead of 11C5, we end up with 1189 by just not messing with any other part of the address. And of course, we loop the binary. We run main again, and now it's waiting for us. Okay. Someone on Twitch doesn't like tmux. You can use screen. To open a new terminal, it's tricky because so you can create a pwn.tools-gdb script as long as it's in your path. That's what pwn.tools will execute. I think. That was the case at some point. You can try to use pwn.tools like that, but it's tricky because you're SSHing into something. You'll have to use either screen or tmux. Can I show the syntax for screen? pwn.tools should automatically detect if you're in screen. Okay, awesome. All right, that brings us to the end of this class time. Thank you for joining. Hopefully we have given you all of the tools. Really, all you really need is that little crocodile-shaped Lego piece that helps remove the bricks. I don't know if you've ever seen this. This thing. Actually, this is the new one. This is even this one looks a little newer. I still have a brick removal piece from the early 90s, like circa 1992. That's all you need to ROP. Hopefully. All right, teaching works correctly. What happened? Was it? Did you regenerate them? Okay, so teaching is currently regenerating. Re-download the binaries. Level 1 is done. The other levels are still regenerating. Sorry about that. We're apparently only human. At least Connor. But remember, if you really enjoy a challenge, that was written by Mahalos. If it's okay, Connor. If it's complete shit and you can't believe it was released by reasonable people, that's me. Okay. Awesome stuff. Isn't that what I said? Mahalo. Oh, mahalos. Mahalos. Mahalos will have. Well, whatever. Yeah, mahalos will have to give me a lesson on the pronunciation of that handle. Okay. Thank you very much. Good luck. Happy hacking, and we will see you on the next stream, which is Friday. It'll be Connor's office hour stream. Until then, don't forget, enjoy the Legos.